So it must be logic, right? So logic is actually supported by the rule base. So any applications that are supported by the rule base, you have an if-else statement. For example, expert system. And then you have act rationally, right? For example, autonomous car, right? Autonomous car. Okay, and then we have cover next the topic, which is the Turing test. So what is a Turing test? Yeah, okay, to test the intelligence of applications, especially for chatbots. Right, we want to test whether this chatbot is able to deceive a human, that it is able to behave like a human. It is able to talk, for example, chatbot. So we have a Turing test. But however, Turing tests tell us that as long as you can respond correctly, right, then it so-called Turing is also called pass the Turing test. But then we have a Chinese room concept used to argue, right? Argue the Turing test. That in order to so-called is intelligent, a machine should understand instead of just memorizing, right? So we have a two theory here, Turing test and Chinese room. Okay. So this is a summary for chapter 1. So let's move on to the chapter 2, which is not relevant at all with this topic 1. Okay, in the chapter 2, we're going to learn a new applications, so-called the PubSearch applications. Anyone from diploma? No. If you are from diploma, then probably you learn this, the breakfasts, deficits, the search strategies. If you are not from the diploma, then this is something new to you. Okay. So in the chapter 2, as I mentioned last week, so we have a chapter 2, chapter 3, and chapter 4. They are under one big topics called PubSearch. Okay, so what is PubSearch applications? One of the famous applications like Waze or Google Maps. Right? Google Maps. Okay, so we have like the Ectal puzzle. So have you played Ectal puzzle before? So it's kind of a puzzle. You have a number from 1 to 8, like something like this. So you have to slide the tiles so that it can restore back to the original positions, something like this in the ascending order. You slide the tiles. Okay, and some other examples like a magic cube. Okay, so you have 6 different colors on each of the surface. Then you have to rotate, twist to restore back to the original state. Okay, so what else? You have cannibals and missionaries. Okay, so this one we're going to cover later. So this is some of the applications under PubSearch. So you're intended to build some applications or solutions for this kind of problems. So before you can solve it, you probably have to do some planning first. Okay, the first step is the planning covered in the chapter 2. You have to formulate the goals and your problem. So this is the kind of a planning stage. So after you do the plannings, then we decide what algorithm to use, right? So this is about algorithms. So it can be blind search or it can be informed search. Okay, this is uninformed search. So this chapter 3 and 4, we will leave it next week, next and following weeks, and week 3 and week 4. So we will just focus in the chapter 2 also. So at the end of this class, we will see some of the partial questions, I think in the slide also, as well as to discuss the answer for the partial questions, which is related to the chapter 2 first. Okay, so yeah, this is the slide. Chapter 2. so as I mentioned earlier, so we have two important stage in order to design some solutions for this kind of applications. The first one is to formulate the goal and the problem, or we call it as a goal and problem formulations. And then after that, we decide what algorithm to use. Blind search, which is no information is provided, and we do the search. Or informed search, where we are given some information, for example, the time, the distance, or some other information for us to do the search. Okay, so we will say the limitations of each of the search as well as the conditions of the information is needed in order to solve using this kind of using that kind of the strategy. Okay, so under the goal formulations, there are three important elements. You're not going to memorize the terms. Yeah, you're not going to memorize the terms, but you have to understand how to define each of these elements. So under the goal formulations, there are three important elements. The first one is the goal. What is your destination, right? For example, you want to build the waste, so you have to get the user go first, right? Where you would like to go? What is your destinations? Like, is it you want to reach in the KLCC, or is it you want to reach in this state? So this is your goal state. So you have to define the first one, goal. The second one is optimal solutions. So optimal solutions stand for what kind of the best solutions that you would like to achieve. So different users may have different optimal solutions. So maybe you would like to reach the destination in the shortest distance. Maybe you would like to reach the destination in the cheapest. Petrol. Okay, so how you define cheapest? So you need this kind of information, right? Cheapest, yes. So you want to reach the destination without the toll, with the least amount of toll, right? You want to reach the destination in the least number of time. So each of the user you have your own definitions of optimal solutions. Okay, there's no fixed answer, but you need user to define first what is their optimal solutions. Okay, so it can be least number of, as I mentioned again, least number of time. It can be a least number of kilometers. It can be least number of so-called toll. It can be a least number of stations, and so on and so forth. Right. So it depends. And then the last one is the abstractions. So abstractions here is referred to the scope. Okay, what are the unwanted or unnecessary informations that you can actually ignore, so that your algorithm can fully focus on to achieve your optimal solutions. Okay, so I repeat again. What is the abstractions? Is the scope. You have to define the scope for what are the unwanted or unnecessary information that you can remove, so that your strategy can fully focus to do the search. For example, your optimal solution is to reach from Thai UMT to KLCC in least number of distance. Okay, distance. So what is the abstractions? You can say that the abstraction here is we will ignore the time taken. Okay, so that you don't have so much information and you don't have so many information for the search to do their task. You remove this unwanted information. I don't care the time taken. I don't care the toll amount. I just want to reach the destination in the least number of distance. That's it. This is my optimal solution. So what is my abstraction? It's the scope. Is that clear? Okay, good. So for example, so now this is the waste. Okay, so you have to define the goal first. So where's the goal? Yeah, this is the goal. You want to reach the standard velocity. So you have to define the goal. So what is the optimal solution? You will see that you have provided the different solutions here. So in this first solution is the least number of time. The third solution is least number of distance. So you may see that this number of time doesn't reflect this number of kilometers. Yeah, sometimes you have jam, sometimes it's a highway, you can drive faster. Sometimes it's a kampong route, right? You have to drive slower, although the distance is very short, but it may take longer time. Okay? Then the last one is the abstractions, the scope. You like to avoid the toll, you ignore the time, you ignore this one, you have to define properly first. Is that clear? So if not clear, it's okay. I'm going to show you 2 or 3 examples and how are we going to define the goal and also the problem later. Okay? So meanwhile, we have these how many? 3, 4, 5, 6, 7. We have 7 elements in problem definitions here. No need to memorize every terms of it. If during the exam, we will definitely ask, okay, define the path, define the code test. We will provide the terms for you, but you have to understand or know how to define it. Okay? So don't memorize it or you have the how many, no need. You just need to know what is initial state, what is successor functions, and so on and so forth. So we have a 7 element here. The first one is the initial state. Where is your starting point? If you like to start from the Thai UMT to reach the KLCC, what is your initial state? Thai UMT. So that is your initial state. Okay? So what is a successor function? Successor function is the most important element in problem definitions. So a successor function is a function to expand, to reach the next state from the current state. Okay, it's a function that helps you to expand to the next state from the current state. For example, you are started from this Thai UMT. So we have this node here. So successor function, you have to define, Thai UMT can go to maybe Wangsa Manju. Okay, from Thai UMT you can also go to maybe Diti Wangsa. Okay, from Thai UMT you can go to maybe Santo. Okay, in other words, it's actually a function that helps you to define all the possible state, all the possible movement from the current state to the next state. So how to define the successor functions? We have an example later, don't worry. But this is the most important element. Right? This is the most important element in the problem definitions. Whether your strategy is able to find the solutions, it depends on this successor function also. Alright. So we have a state space, right? State space. So state space is overall picture. The stage that can be show all the possible state. Okay? State space is a space, it's actually a space to show all the state, from the initial point to the ending point. It's like a map, right? To show all the states. So we have an example later. So go test normally we use if-then statement, right? Whether to check whether your current state is it equal to the goal state first. We have to, every time you expand the node, you have to use the if-then statement to check whether this state is equal to goal state. If not equal to goal state, then we continue the search. If equal to the goal state, then we will stop the search. So this will be the solutions. Okay, we have a start cost. Start cost is the cost. Yeah, it's the cost from one state to another state. So this is the start cost. From one state to another state is stand for start cost. And the start cost is defined by you also. It depends on the optimal solutions. If your optimal solution is about time, then the start cost here is the unit for the start cost is equal to maybe seconds or maybe minutes. If your optimal solution is to reach the destination in the least number of distance, when we talk about the distance, then your start cost will be in maybe meter or kilometer. What is the distance? This is the start cost. What is the cost from one state expand to another state? And the cost is depends on your optimal solutions. Okay? And the last one is the path cost. The path cost is the total start cost from along the path. For example, you have expand here, expand here. So what is the path cost from this? So you got to add the start cost from one state to another state. This is the path cost. Is that clear? Okay, not clear, doesn't matter. So let's move on to one of the examples. So we have this map here. So we have a Thai UMT. You can go to the KLCC. So you can go to the Wangsa Maju. So Thai UMT can go to the DD Wangsa also. Then eventually Wangsa Maju and DD Wangsa, you can reach KLCC. So there are three paths. Right, there are three paths to reach KLCC from Thai UMT. And this is the information that's given. So we have a distance, 15 kilometers, 13 kilometers, 3 kilometers, and so forth. Maybe you have other informations which is not inside this map. Maybe you have time, maybe you have about weather, maybe you have a route condition, but there are too many information. I just simplified, I just provide you the distance at this map. Alright. So let's see how to define this map. Okay, using the how to define or the goals, the initial state based on this map. Alright. Let's go element by element. So what is the initial state based on this problem? Yeah. Thai UMT. Louder? Thai UMT, okay. So just don't worry about this. This is just a way how you represent this knowledge. You can define your own method, just like a pseudocode, right? You can use move, right? Or you can use go, right? So this is 0 means stand for no, you're not moving anywhere, right? So this is the destination, but you don't have destination. So you just want to represent the initial state. So this is Thai UMT. Okay, you can write from also. It's just a way how to represent your knowledge, right? It doesn't matter. Okay, so this is show the initial state. It's Thai UMT, very good. So successor functions, as I mentioned, successor function is to show all the possible movement from one state to another state. So if based on the map here, if you based on this map, you can see that Thai UMT can go to the KLCC, Thai UMT can go to Wangsa Maju, and Thai UMT can go to DD Wangsa, right? So you have to define the successor function first. Yeah, something look like this. If you look at this, Thai UMT can go to here, here, here. So how to write the successor functions? You can use this way, or it's up to you. You can use the go, whatever. So we just want to define, okay? From Thai UMT, right? From Thai UMT, you can reach KLCC. So this is one of the possible movement from here to here. It takes 50 kilometers. So second successor functions is you can start from the Thai UMT. You can reach Wangsa Maju. It's 3 kilometers. And the last one, you can have Thai UMT. It reaches the DD Wangsa, 8 kilometers. So these are the three possible movement from Thai UMT to 3 different states. Then you have to define from Wangsa Maju, you can reach to KLCC. Then you have to define from here, from the Wangsa Maju to here as well. Then you have to define all the successor functions. So later on, during the code, you have to write this code so that during the movement, we will based on this code move the agents, right? Move the agents. Okay. So, but however, we are not going to cover this in the practical due to the time constraints. It's possible then we will cover. Otherwise, then we will just cover the theory. Okay. So this is successor function to solve the possible movement from one state to another state. All right. The last one, not the last one. What is the? Oh, what is the ghost? Go formulation. Moment. Oh, okay. And the go formulation is here. I missed out this slide. Okay. So this one. So this one should be somewhere around here. Okay. So based on this map, what is the goal? So the goal is you want to reach the KLCC. So what is the optimal solutions? So it's up to you. You want to reach the destination, the least number of distance. But based on the information given, we got only the distance. So one of the optimal solution is to get the shortest path. to KLCC, right? Okay. If let's say you don't have this distance given, then maybe the optimal solution is you would like to reach the KLCC in least number of stations. Okay, least number of stations. So this is considered station 1. So this is one station. If you go through the second path, you probably go through one station and then second station. You have to go through one station. Okay, total 3 lah, 1, 2, 3. If you take this path, 1, 2. So this path, 1, 2, 3. Is that clear? Right. So it's up to you. So you can define in the least number of distance, or you want to reach the destination in the least number of stations. Do you want me? The number of stations is not equal to the distance. Okay. The station means that, let's say now you have this state A. So we have B, we have C, we have D here. Okay, so if your optimal solution is to reach the destination in the least number of stations, then it means that this is considered one station. If you take this path, then the total stations is equal to A and D, 2 stations. If you take this path, then you may 1, 2, 3, 3 stations. You will take the last path, also 3 stations. So this is about stations. It's not related to distance. It's about stations. Okay? So what is the abstraction here? Abstractions. Any scope, any information that you can ignore so that your algorithm can fully focus to do the search. In this case, what is the abstractions? Abstractions. And to test your understanding. Yeah, anyone. You don't want. Oh, 1K. Yeah. KLCC. Abstraction is KLCC. Sure. Not sure. Time, okay. Right, so the time is not our concern in this case. So that will be an answer. What is the abstraction in this case? Time is not our concern in this case. Right, okay? Maybe the weather is not our concern in this case. The road condition is not our concern in this case. Which this factor will probably affect the time or the durations or the distance, but you temporarily ignore this kind of factors first. Okay? So, right, so that is the state space. As I mentioned, state space is the space that consists all the state from the beginning until the end. So if you look at this initial, this is the map here. So we can see that from time UMT, normally the initial point we will put at the so-called the level 0. Okay, level 0. So the time UMT can expand to the KLCC, can go to the Wangsa Maju and D Wangsa. So we have 3 branches to show we have reached this destination from this state. Yeah, from the time UMT you can go to the KLCC, you can go to the Wangsa Maju, and you can go to the DD Wangsa. So from KLCC you cannot expand because that is the destination, you cannot expand. So how about from Wangsa Maju? From Wangsa Maju you can go to the KLCC, at the same time you can go back to the time UMT. So you have 2 branches here. So DD Wangsa you can also go back to the time UMT, or you can go to the KLCC. So you have 2 the so-called expanded node or the child node. So this is the state space. It's a space consists of all the possible movement, possible state from the initial point until the end point. Okay, it's a space. Path is nothing special. Path is just to show how should we display the path. Right. For example, in this case, right. So this is how we display the path on the maybe your UI. You can go to the time UMT on some module KLCC. So this is the path shown by it shows the step-by-step path from this stage to the maybe the next stage. So how should we going to display? Are we going to display the distance as well? Yeah. And the last and this code test, as I mentioned, you can use the else statement. If you don't use this state, also you can use another way to display. For example, you can check. Right. You can show if the current state is it equal to the goal state? If yes, then maybe you show path, maybe you return path. Right. So this is one of the example how you can define the goal test using. Normally we use if else statement. The reason we have to include this goal test is we don't want the search to continue to search, right? For example, now you want to reach the KLCC, so that is your goal. So we don't want the algorithm to continue search. Okay, Wangsa Maju reach KLCC. Okay, KLCC continue to search. We don't want this to happen. We want the algorithm to know that, oh, this is the goal, right? This is the goal, KLCC is the goal. If we expand search, oh, we reach the KLCC, we just stop here. So this is our path. So we need a goal test to always check whether your current state is equal to goal state or not. If equal to goal state, we don't do anything more, right? We just stop it there. Okay? Start cost, as I mentioned, is a cost that travels from one state to another state. In this case, since our optimal solution is to find the path with the least number of distance, so that the cost applied here is in kilometer, is the distance. So then we can see that the TBR go to the Wangsa Maju is 3. Right? Okay, from this state to this state is 3. From this state to this state is 13. So what is the path cost? Is the total cost along the path. So let's say now we would like to calculate the path cost travel from TBR to KLCC. So you just add up together. So the path cost will be 63 plus 13, 16. Okay, so this is how we define the problem angle. Right, it's not that difficult, but however, still a lot of students make a mistake here. So maybe we try another questions, another examples here. So your goal is to travel to fetch these 3 cannibals and 3 missionaries from the left hand side to the right hand side. So before we do all these things, maybe we can represent first this situation in a string format. Okay, so one way you can define or express in these representations, maybe I can say you have 3, then the boat positions, the number of cannibals and number of missionaries at the right hand side is 0, 0. Maybe I will represent this situation using this expression first, so that everyone can understand. So that I don't need to write, okay, you have 3 missionaries, 3 cannibals at the left hand side. I know the write so wrong. Instead, I just represent inside this format. Okay, so it means that you have a 3 cannibal and 3 missionaries, this one at the left hand side. So this is the boat positions. So these 2 are actually the this one number of cannibals, and this one is the number of missionaries at the right hand side. Easy. So that if, let's say now, based on that situations, I would like to move 2 cannibals to the right hand side, then I can just write 1, 3. The boat travel to the right mark. Right. Then I will just write this expression. That's easy to understand. Right. Okay. So this means that if I move 2 cannibals from left hand side to right hand side, then this is the expression. So I just minus 2 now. Just now we have 3 cannibals. Now I move 2 to the right hand side, so I have to minus 2. So it left 1. So this one 0, I have to add 2, become 2. So this is the expression. So where we have 2 cannibals move from left hand side to the right hand side. Okay? Is that clear? This case. Okay? So what is the goal? Then I can say the goal is to reach this 0, 0, right, 3, 3. So this is my goal. This is my initial state. So you can have your own way to define. It's up to you. But for me, I will use this way. Okay, you can use your own method to define these situations. Is that clear? Okay. All right. So this is the initial not yet. So this is the goal, right? So we have what optimal solutions. So what is the optimal solutions? Right. Go back to the previous questions, right? Previous case. What is the possible optimal solutions that we would like to achieve these situations? The food? That one is your condition. That one is your objective. You don't want to let the missionaries eaten by the cannibal. That is your goal. That is not the attraction. That is not your feasible solution. Feasible solution, what is the best solution? What is the best solution that you would like to achieve in this case? Yes. You would like to use least number of steps, or maybe I will call it as 3. How many trips? Right. 3. To reach the goal. Right. So I would like to use the least number of steps. I don't want to use just now. I had to try and error until night. Right. So I want to use least number of trips to reach the goal. That's my optimal solutions. Okay. What is the abstractions? What is abstractions? What is the unwanted information that you probably can remove, so that we just focus on how to use the number or least number of trips to reach our goal. Any factors that may affect the performance, but you want to remove. Any other factors? E1, I still remember that. What's the attractions and its groups? What is it? Huh? Person on the board. The person on the board. The person on the board for what? Huh? Oh. That one is your rules. It means that the number of person on the boat. That one is the conditions. That one is the rules. Rules is different than the abstraction. Rules is we have to follow the rules to play this game. So what is the abstractions? Abstraction is what are the unwanted information that you want to remove. I'll give you one example, maybe the weather. The weather. The weather, whether it's a raining day, whether it's a sunny day, it will affect the performance of how you row the boat, right? But we ignore first. We ignore these factors. We don't care about what is the weather, whether it's a raining day, whether it's a night mode, whether it's a daily mode. The speed that you row is all the same, right? Everyone know how to row the boat. The speed is the same. We don't care the weather. We don't care the speed of the streaming of the river. This is the abstractions. Okay? Okay. Right. So we don't care the weather. In this case, the abstraction is the weather. One of the example lah. Oh my goodness. So how to define the abstraction? You have to think what are the factors that may affect the optimal solution. What are the factors that may affect your optimal solution? Like the previous case, the drive, right? So we want to reach the destination in the least number of distance. So what are the factors that may affect it? Maybe the toll, right? The road condition, maybe the time. But all this we ignore first. So the things that you want to ignore, put under abstractions. Same goes to this one. Okay? So let's continue. Okay, so what is the initial state? So now we come to this is the done for the goal formulation. So now let's move on to the problem formulation. So under the problem formulations, so the first one is the initial state. Initial state. So initial state is equal to this one. So we have 3 cannibals, 3 missionaries at the left hand side. The position of the boat is the left hand side. the number of cannibals and number of missionary at the right hand side, which is 33L00. Okay, so that is your initial state. So what is the successor function? Okay, so successor function is the possible movement change from one state to another state. Okay, so what is successor function? So in this case, you can say you want to move two cannibals from left to right, right? If you move two cannibals from left to right, then you can say, right, move two cannibals from left to right. So this is one of the possible movement. What are the possible movement? Move one cannibal from left to right. You can also say move one cannibal, one missionaries from left to right, and so and so. What else? What else? Move one missionaries from left to right, move two missionaries from left to right. You can also say move two cannibals from right back to left, move one missionaries, one cannibal from right back to left. The one will be your successor function also. So you have to list out all the possible movement in this case. Is that clear? Okay, all the possible movement, right? Okay, one missionaries from from left to right, two missionaries from left to right, and then you can move two cannibals from right to left, and so forth. So you have so many successor points. You have to define it in your coding later. Okay, so that is your successor functions. So what is a state space? State space will be the space that consists of all the states. Consists all the states. So for example, you have initially you have 3 here. Okay, you have 3. So we can move two missionaries from left to right. This is one of the possible. And then you can also move one from left to right. Then you continue to expand until the end. But this is not the complete state space. So you have to expand until the end. Then you will have a full state space. I think we have this in the tutorial questions, if not mistaken. Right. And then what else do we have? Right. Okay, so this is the state space. We have all the path into the solution. We will cover this next week. And then the path is how you show the state travels from one state to another state. So this is one of the methods. Okay. And then you have a go test. Normally we use the if else statement. So something different here. You can use the if else statement that I explained right earlier on. Check whether it's the current state equal to the goal state. If yes, then you stop the search. Then we have a cost. The start cost is, in this case, is number of trips, right? The number of trips. So the moment that you travel from the left hand side to the right hand side, the start cost is equal to one trip. Okay. Meanwhile, what is the path cost? Is the total number of start costs that change from one state along the path. From one state, move. Then you have to calculate the total start cost. Okay. Let's say now you have this one. You travel here again, you travel here again. So what is the path cost for this case? 1 plus 1 plus 1. The path cost is equal to 3. But the start cost is equal to 1. Why? Because you're going to change from one state to another state. That is start cost. That's why it's called start cost. Change from one step to another state is the start cost. Okay? Boleh? So far, any questions? Definitely there will be one question ask you to define all these things later. Okay, so since all of you feel less sleepy, so I give you 10 minutes of rest. Yeah, so we will come back. I don't know how to call it. It's like a square. Then you can slide the tiles, right? So then you can mess it up, and then you have to think how to slide the numbers to arrange all these number back to the ascending orders, right? 1, 2, 3, 4, 5, 6, 7, 8. So how many of you played this game before? Or maybe I think you have this game on the phone also, right? You have some apps. So yeah, so again, before we design the algorithms using the blind search, you can use blind search or informed search. We have to define the problem and goal also, right? Like the previous examples. So in this case, again, you can use these representations, this nice square here, to define your goal problems. Or another way that you can define this 9 tiles here is you represent it in the list. For example, in the initial state, you can represent this way: 1, 4, 5, 2, 3, 7, 6, 8. And then the empty tiles I normally represent it as 0. Okay, so this is referred to the first row. So this is referred to the second row. So this is referred to the third row. So this is referred to the first column, second, and third, as well as this one, right? So easy, right? You have this list, then it's understood that this is first row 1, 4, 5, 2, 3, 7, second row, and 6, 8, and the 0 represented the empty tiles. Okay. So yeah, let's define our goal first. So what is the goal? Yes, very good. So your goal is to reach 1, 2, 3, 4, 5, 6, 7, 8, 0. So this is your goal, right? And then what is your optimal solutions? Yes, you would like to reach the goal with at least a number of steps. So the step here is referred to the slide, right? One slide is equal to one step. So the last one, abstraction. So what are the factors that may affect maybe the speed of your slidings? What are factors that you think that will affect? The weather. Can you further elaborate how the okay, the directions, the sliding. Sliding is the requirement, is it? You slide. The time taken. Okay, you can say the time taken is not our main factors, right? As long as the least number of steps. Maybe some of you are very slow, then you slide slower. Maybe some of you are very fast. The time is not our concern. We just to reach in the least number of steps. Very good. Time is not our concern. Someone said weather. You can write weather in the exam, but you have to elaborate. Why weather? Maybe it's raining day, you're moody. If you're moody, it will affect. Yeah. Can but see the marker lah. If the marker is very good, then you give you marks. If the marker is very strict one, then it will give you marks. Okay, time is not the concern. Maybe the materials. Maybe the materials of the cube is not our concern. Some made of wood, some made of plastic, right? Plastic sometimes you kick, you know, right? Jam. So in our case, the materials maybe is not our concern. Okay, maybe it's not our concern. Okay, and others. So you have to think what are the factors that may affect the performance, may affect the optimal solutions. So done. So you have 3 marks here. So what is problem formulation, right? So we have an initial state, right? So initial state. So this is the initial state. 1, 4, 5, 2, 3, 7, 6, 8, 0. Okay. So what else? What are elements in problem formulations? Yeah, Brenda. What other elements inside? Pardon? element inside the problem formulations. What other things may we have to define besides initial states? Okay, step cost. What is step cost? Equal to? Actually it's a number. It's a step cost in this case. 1. Yeah, because every time you slide, it's equal to 1 step. You cannot slide 2 times, right? You have to slide 1 time each step. Okay, step cost is the cost is taken to change one state to another state or the next state. Right? For example, in this case, you slide 7, right? You slide 7 down, then it's equal to 1. Okay. So what else? You have a path cost. So path cost is the total cost along the path. You can write like this because in this case you don't have the exact path yet. What else? Successor function is the most important element. What is the successor function? It's all the possible movement, right? So what are all the possible movement? Okay, you can say move 7 to 0. What else? 8 to 0. 3 to 0. You don't look at the initial state. It's a possible movement. 3 can move to 0, right? But you don't look at the initial state. Successor function is all the possible movement change from one state to another state. It doesn't matter it's from the initial state or any other state. It's the possible movement. What are the possible movement do you think? You can move 1 to 0, 2 to 0, 4 to 0. Then you can move 1 to 1, 1 to 2, 3 to 2. Oh, sorry, 3 to 0. Okay, sorry. 7 to 0. You can move. What else? 8 to 0. Anything, right? You can. There will be many movement, right? A lot of movement. So this make our move is not effective. So instead of moving the tiles to 0, in this case, we move the empty tiles. If you move the empty tiles, then there will be only 4 movement. Right? You can move 0, right, up, left, up, and down, down. So that is your successor function. You have only 4 steps. Easy. Instead of you move so many steps here, you just control the empty tiles. Instead of move the value, you move the empty tiles. I know that in exact ways cannot write, but in the algorithm, yes, you move the empty tiles to left, to right, to up, or to down. There are only 4 possible movements. Is that clear? Yeah, so you can move this to here, this to here, maybe this one is outside the boundary, so we cannot move. So outside the boundary, we cannot move. So this will be your successor function. Move the empty tiles to left, to right, to up, or to down. Okay, so what else you have? You have a state space. So let's see how do we expand, or how do we generate the state space. Maybe I give you some ideas. Yeah. Okay. Let's say we set some sequence. We set some sequence. Okay. 0 move to right. 0 move to down. 0 move to left. 0 move to up. We follow this sequence. We have to set a sequence. So let's see how do we generate the state space. So this is the initial state. Start from level 0. Okay. Okay. So try to use the successor function here. See whether we can move this empty tile. This empty tile 0. Can we move to the right? Can we move to the right? Cannot, right? It's actually the boundary. So no. So we have to go to the next successor function. Can we move down? Cannot. The third successor function, can we move left? Yes. If you move left, then you probably generate this state. Okay, done. So next, same level. We're talking about same level. Okay, so next, can we move up? Yes. So if you move up, so we will get 1, 4, 5, 2, 3, 0, 6, 8, 7. So do we have more successor functions? No, right? So you can see that successor function is to generate this state to another state. The purpose for successor function is for you to move to another state, move to another step. Okay? So this is the possible child node from this parent node. So now, done. No more possible action already. No more. Okay? So restart the successor function, generate from here. Can we move the 0 to right? Yes. So we have 1, 4, 5, 2, 3, 7, 6, 8, 0. Can we move down? No. Can we move left? Yes. Okay. The last one, can we move up? The last successor functions. Can we move up? Can. So if you move up, so we will get this. Yes. So this 3 will be the child node generated from this parent node. Then we continue with this state. Can we move right? Cannot. Can we move down? Yes. Okay. Can we move left? Can. Okay. Can we move up? Can. Right. Can we move? We can move out. No more. Then we have to continue generate until the end, until there's no more expansions. That will be your state space. But we won't ask you to generate the state space now. Normally, if we would like to generate, then we will say, okay, generate the state space until level 2. So this is level 0, level 1, level 2. Expand here, then you stop it. Okay? So normally. Okay? So that is the state space. What else? We have a state space, successor functions, initial state, path. I think the path is not very important. Path to show the how you display the path. Then we have a go test. You use the if else statement, whether the current state is equal to goal state. If yes, stop it. If no, continue. Okay, so successor function done, state space done. Define the path. Yeah, so this is how you display the path. Go test. You can use the if else statement. Step cost. The step cost here is equal to 1. Because every time you slide here, slide the step cost. I think someone defined here the step cost is equal to 1. So we talk about the path cost, right? The path cost, you can give one example. The path from this state to this state is equal to 1 plus 1. So the path cost for this path is equal to 2. Okay, means that you slide 2 times. You slide this 0 to left, you get here. 0, move back to right, so you get 2. So the path cost for this path is equal to 2. You slide 2 times, so the total step cost is equal to 2. Alright. Okay. Okay, let's move on. So after you define the goals and as well as the problem, the next thing that you have to do is, no more. So you have to apply the search, right? The search algorithms, which we will cover next week and the following 2 weeks later. So then after that you execute. You start to find the solution using the algorithms. So to search the algorithms, there are many ways. You can use a search tree. You can use a search graph. So the difference between the search tree and the search graph is the search graph can generate the same state from the multiple paths. So shown at here. So this is how the search tree works. So next week onward, next week and also the week 4, I will show you how to generate the search tree using the search algorithm, blind search and uninformed search. Forget about the search graph. I'm not going to show you how to display the search graph. It may confuse you, so I will just focus on this technique. So how to generate the resulting tree as well as the search tree. Okay, and well as the return path and the source path, everything, so I will cover. So this is search graph, forget about this, so I will just focus on this. And some of the terminologies that you may need to know. Okay, so we have this, for example, TBR, right? So TBR here, normally we will call this as a parents node, right? It's the parents node. So this parents node, for example, this is also called as parents node. We will generate these two child nodes, right? We will generate two child nodes, right? So this child node, the moment that it expands, so this child node now become parents node. So we will change the name to parents node. So it will generate 3 child nodes. So this expanding means that you expand the moment they expand. So we have this terminology, so expand. Then we have a fringe here. Fringe is actually like a storage, right? It's a storage to store the nodes that is going to expand. For example, the moment I expand, I need a space. I will in the coding later, you need to generate an array or a list to store. Right? You need to create an array to store this state inside here first. To store this state inside here, so that after the moments you can't expand anymore, then we will retrieve this state to continue to expand. So these 3 states here you store inside the fringe again, frontier, or sometimes we call it as a frontier, sometimes we call it as a fringe. It's just a place to store the state so that you can expand later. Okay. Then we have a leaf node. It stands for the leaf or the node that doesn't have any child node anymore. It's a dead end. Right? For example, just now, somewhere around, you expand A, expand B, maybe expand C, expand D. D is a dead end. So this dead end is here, we call this as the leaf node. This is a leaf node. It's a node that there's no more child node that you cannot expand anymore. Just some terms. Okay, so in the search algorithms or the problems, normally we have to avoid repeated state. So what does it mean by repeated state? So assume that you have this graph, you want to expand, right? Just now, this one. This one is actually repeated node, right? See, you have a, let's say now you have a state A. You expand, you have a B, you have a C. So look at this D here. D is actually equal to the A, right? So you will see that this is actually repeated nodes. So in the search algorithms, normally we have to write a program in such a way we don't want this repeated nodes. If you have a repeated node, you are wasting your time. You are repeating this again. You're repeating this 1, 4, 5. You have a 2, 3, 7, and 6, 0, 8. You repeat again. Then you repeat. So it's kind of wasting your time and the memory. So in the search, we avoid repeated state. Okay? We have to write a program in such a way we have to detect whether it's already expanded. If yes, then we remove it. We don't want to have a repeated nodes. Okay? So after we perform the search, so how do we define whether this is a good search or whether this algorithm is good based on these 4 criteria? Whether this search gives you completeness means that able to return you the solutions. We probably don't want an algorithm that they fail to return you the solutions, right? So we want the algorithm that guarantee completeness. Whether this algorithm provides the optimal solutions or not. Some algorithms you may see next week, or next week, we have a depth search to show that it's able to return you the solution, but it's not the optimal solutions. We have this kind of solution. We have this kind of algorithms. And then in terms of times, whether is it using a least time or how much memory that you use. So we will base on these 4 criteria to assess the strategy. So this one we'll cover next week. So these one are examples. So let's see this one of the past year questions back to 2021, 2020 October, 2 years ago. Yeah, 2 years ago. So you will see that an intelligent system defines the shortest path from S to G. So station figure 1 shows the directed graph. Each stations. So you have this table 1, some other informations. Formulate the goal and problem above. So what is the goal in this case? S goal. G, yeah. Yeah. I think the question is stated here. From S reach to G. So what is the goal? Definitely is G lah. What is your optimal solution? Shortest path, yeah, shortest distance. What is your abstractions? The times, the values, the load condition, the toll, okay, and the problem formulations. What is your initial state? As bonus mark, the questions give you the answer. What else? Successor functions. Successor function in this case is okay. This one is actually using a star. It's one of the strategies in the informed search. So forget about the successor function in this case. Step cost. Step cost is, for example, S to A, 3. The path cost, you can give one example. The path cost from S to C, for example, 3 plus 3, you have 6 here. Okay? So what else? You have initial state, successor function, path, yeah, how to display the path, step cost, path cost, you finish. Done. Then you get 8 marks. Easily, yeah, 8 marks. How about this? Another similar questions. In December examination, it's a short sem. So again, S to G. So same questions. So initial state S, goal state G. What is your optimal solution to reach the destination in the least number of distance? Right? Abstractions, the times can be ignored. Yeah. Is it? Okay now. So I think the answer is given here. The answer is given here. If you look at your slides, the answer is inside the comment box, so you can just do revision on later.